The graph above represents the potential energy U as a function of position R for a particle of mass m. If the particle is released from rest at position R naught, right here, what will its speed be at position 3 R naught? So this is an energy conservation problem. So we have our graph here. This is where our particle is released at R naught. At this point here is R 2 naught, no 2 R naught, and its potential energy there is U naught. We want to find its speed at 3 R naught, which is right here. So basically we just write our energy conservation problem out, which is initial potential energy plus initial kinetic energy equals to final potential energy plus final kinetic energy. And we know our initial potential energy is 3 U naught right here, right here. So we just write that in. Plus our initial kinetic energy is 0 because at our maximum potential energy, our initial kinetic energy would be 0. Our final potential energy would be U naught, 2 U naught. Because our final potential energy would be right here, which is 2 U naught right here. So we write UF to be 2 U naught. Our final kinetic energy would just be 1/2 mv squared because we want to find the final velocity when the particle is at 3 R naught, which isn't a problem, which is what we're trying to find. And we know that final kinetic energy would just be 1/2 mv squared, and we want to find the final velocity. So we find final velocity by finding which is in the final kinetic energy. So basically we just move around stuff, and 3 U naught minus 2 U naught equals to 1/2 mv squared. We subtract this, which we get U naught equals to 1/2 mv squared. We multiply by 2, so it's 2 U naught equals to mv squared divided by m, u square root. So v would be square root of 2 U naught divided by m, which is our answer C. Question number 2. A 10-meter long vertical canyon is used to accelerate a 1 kilogram ball straight up into the air with a constant force of 13.2 newtons. It is used to accelerate the bowling ball up the length of the canyon. What is the ball's approximate velocity as it leaves the canyon, assuming no entry of friction? So basically, before we start, we have to identify all of our variables. So we know mass for the ball is 1 kilogram. Force done on the ball is 13.2 newtons. The length is 10 meters. So we know work is equal to change in energy, and change in energy is basically change in potential plus change in kinetic. So we can connect this to this. We can substitute what we have for change in energy with delta U plus delta K for our work. So work is equal to change in potential plus change in kinetic energy. We do this because we want to find the velocity in this case, and to find velocity we have kinetic energy here to find the velocity. So we write force times distance equals to mgh, since we don't take into regard of the final gravitational energy because that would just be 0, plus 1/2 mv squared. We don't take into account of initial kinetic energy because in that case initial kinetic energy would be 0. And we just plug in everything we know. We isolate for v first, and then we plug in everything we know. So v turns out to be square root of 2 times fd minus mgh divided by m. So v equals to square root of 2 times 13.2 times our distance, which is L right here, equals times 10 minus mgh minus m, which is 1 in this case, times g, which is 9.8, which we just say 10, times our height again, which is 10, and then divided by m, which is 1 in this case. So our velocity turns out to be square root of 2 times 32 divided by 1, which gives us 8 meters. per second, which is the answer E. The potential energy function U of x is associated with a conservative force F and described by the graph given here. If a particle being acting on by this force has a kinetic energy of 1 joules at position x naught, what is the particle's kinetic energy at position x sub 4? So again, this is similar to question number 1. This is an example of energy conservation problem, and the total mechanical energy of the system remains constant. So we can just write delta Ui plus Ki equals to Uf plus Kf, because the energy that we start with is the same as the energy that we ended with. So Ui in this case would be 4 joules here. So 4 joules plus Ki would be 1, since in the problem it stated if a particle being acted on by this force has a kinetic energy of 1 joules at position x naught, which is here. So plus 1 joule equals to Uf, our final potential energy at x sub 4 is negative 2 joules, plus Kf, which is what we want to find. What's the particle's kinetic energy at position x sub 4? So just move everything around. 4 joules plus 1 joule plus 2 joules equals to Kf. So Kf equals to 4 plus 1 is 5, 5 plus 2 is 7 joules. Our answer would be B, 7 joules. You are to perform an experiment investigating the conservation of mechanical energy involving a transformation from initial gravitational potential energy to translational kinetic energy. You are given the equipment listed below. All the supports required to hold the equipment and a lab table. On the list below, indicate which piece of equipment you would use by checking the line next to each item. So it doesn't matter what we pick. We should pick meter stick and stopwatch. We can get track, cart, and string, but the reason why we need meter stick and stopwatch is because we need to time how long it takes for the object to go from one place to the other, demonstrating kinetic energy and potential energy. And we also need the meter stick to calculate the distance traveled or the height of the object to find the gravitational potential energy. So A, we're done with A. Part B. Outline procedure for performing the experiment. Include a diagram of your experimental setup. Label the equipment in your diagram. Also include a description of the measurements you would make and a symbol for each measurement. So for my experiment diagram, it's basically like this. It has a triangle. It has a cart on one end. It's at a certain height, h, and the distance from the top of the ramp to the end of the ramp is a distance d. So we would use the electronic balance to calculate the mass of the cart. Mass of cart. We would set the track at an incline and measure the height h. So height h. We would also place the cart at the top of the incline. Place cart at top of incline and release from rest. So that's step 1, step 2, step 3. We would use the stopwatch to measure the time t it takes for the cart to move down the incline. So use stopwatch to measure time from top of ramp to bottom. And number 5, we would measure the distance d that the cart moves down the incline. Okay, so part C. give a detailed account of the calculations of gravitational potential energy and translational kinetic energy, both before and after the transformation, in terms of quantity measured in part B. So, in this case, initial gravitational potential energy would be U G naught. That would just be simply mgh. Our final gravitational potential energy would just be U gravitational F, which is just 0, because at the bottom of the ramp we have no potential energy, but at the top of the ramp there is potential energy because we have height h. And our initial kinetic energy, which is K naught, would just be 0, because at the top of the ramp the cart isn't moving, so we have 0 kinetic energy at the top of the ramp. Our final kinetic energy, Kf, would be 1/2 mvf squared, because right before the cart hits the floor, or right before the cart gets off the ramp, it has kinetic energy because it's moving down really fast, and the velocity there would just be vf, because that's where our final velocity would be the greatest. It's vf, what just the instant before the cart gets off the ramp. So our acceleration is constant. So according to one of our kinematics equation, would just be d equals to 1/2 v naught plus vf t, which would just give us v naught plus vf times t over 2, and that's just acceleration, simple acceleration. So our vf in this case would just be 2d over t. Part D. After your first trial, your calculations show that energy increased during the experiment. Assuming you made no mathematical errors, give a reasonable explanation for this result. So when your energy increased, that just means we started off with more energy, and the reason why we started with more energy is because our potential energy would be greater at that point. But potential energy can't possibly be greater at that point, because it's just gravity doing the work. So one of the flaws of this experiment that resulted in an energy increase would just be because we have an unintentional push of the object onto the cart, I mean. As a result, we would have increased initial energy, right? Because energy is never destroyed or created, it's just transferred. So the result of having more energy to start with, we will have more energy to end with.